So for second part B, we're going to prove that this ring is commutative. And of course, when we talk about the ring being a commutative, we are talking about it's being commutative with respect to the multiplicative with multiplication itself. Because for addition part, we already suppose that it is commutative already, or is abelian. Then if we want to show that R is commutative, what we can do is, of course, we need to show that we want to show that AB is equal to BA for all A and B in such ring. So that we will prove all those possible possible cases, and makes it and all of them are necessarily be commutative in order to prove the whole ring is commutative. How should we do it? Well, we can see that if we start from the left hand side, AB, we actually get that AB is equal to AB quantity squared using the condition that we have, and any elements inside is equal to the elements squared. And of course, we know that if A and B are elements in R, the product here is also an element in R, because R is a ring. So it is closed under multiplication. So in this case, we will actually get AB squared, which is same as AB times AB. And then now we can break it down into AB like this. And you might think it is isn't this obvious? Well, it's not always true for some kind of algebras, but this is actually true in any ring, because in ring the multiplication part has to be alternative, meaning that it's associative, meaning that it doesn't matter which part we multiply first, we will still get the same result. And so in this case, we will be able to say that instead of multiplying A and B themselves together first before we put them together, we can just break it down and then regroup it in the following way, like this. So what does that do to our proof? Well, now we're going to take away the A on the left side, meaning that we're now going to let's put it on the right side as our intermediate results we have. So as we have this expression here, we're now going to try to undo the A on the far left hand side on both sides by multiplying with A inverse here. Then as we multiply A inverse on both sides, we're going to get on the left hand side the A inverse and A will be cancelled out, so that we only have a B remaining. Where on the right hand side, of course, the A inverse and A that are next to each other will cancel out. Again, that's based on the associativity, that we can just multiply in any order we want, such that now we only have B, A, B left. Next, we're going to multiply with B inverse on both sides. And this time, instead of multiplying it to the left, we're going to put it on the right side, doing a right multiplicative, like so. Now, why do we not want to put it on the left? Of course, if we put it on the left, on the left hand side, no matter what, we will still see that they're gonna be cancelled. So that we will just get the identity 1 here, and again, there's a multiplicative identity. Okay. Now on the right hand side, suppose we put this put the B inverse on the left, then it will cancel with the B that we start off, and then we will get AB back. But that is not what we want to prove. We don't want to show that A times B is equal to 1 here. So what we are going to prove is that we're going to show, we want to put it on the right side, such that Now we will be able to cancel out the the B and B inverse here to get that 1 is actually equal to BA. Now you may ask that this is still not what we really want to prove, right? Well, because we're kind of like did something, we did a lot of extra steps ahead here. What we are actually going to do is we can actually try the following way. We can show that by here we can